Hello, math students. Composite functions. Evaluate the function below as indicated. H of t is equal to 3t squared plus t. H of negative 2 means we take this rule and we replace the t's with negative 2. So it would become 3 times negative 2 squared plus a negative 2. And we get 3 times 4, that's 12, plus negative 2, and we get 10 out of this. H of 3a. So if we change this t right here to 3a, then we change both these t's to 3a to use the rule. So h of 3a will be 3 times 3a squared plus 3a. And that's going to give me 3a times 3a is 9a squared, but then times the other 3, so we have 27a squared plus 3a. And we could factor this, but I'm not going to. And then finally, h of x minus 4. So if I change this t here to x minus 4, then make sure you change both these t's to x minus 4. And use parentheses, especially on this one here. So we get 3 times x minus 4 squared, and then plus x minus 4. Now we could spend the time to FOIL this. We'll do this really quickly. When I FOIL this one here, we're going to do x minus 4 times x minus 4, and then triple everything. So go in that order. We're going to get 3x squared. We're going to have minus 8x, but then triple that, so minus 24x, and then plus 16, but triple that, so plus 48. And then we have this x minus 4, no longer need parentheses on there. And then you can combine similar terms. So we get 3x squared minus 23x plus 44. This was just review of function evaluation. Also, I should say that the t over here is sort of a dummy variable, meaning that it could be any letter. I could have called this function h of u is equal to 3u squared plus u. And it would represent the same function as far as what it does to inputs. Now the t and u might mean different things. Maybe t is time and u is something else. But as far as what this function does to inputs and how it converts outputs, the calculation is the same. So we say it's the same function h. Okay, now given two functions f and g, their composition or composite function is defined as follows. So we have this f little circle there and then the g of x. This is read f of g of x. Sometimes read fog of x. And what it means is that you do f of g of x. So it means you evaluate the function f at g of x. So you take g of x and you plug it into the inputs for f. Okay, so using these two functions here, f will be x squared minus 2x and g will be 3x. Let's go ahead and practice what fog is for this particular case. So I'm going to rewrite this as f of g of x. And what we're going to do is we're going to take the g of x function, which is 3x, and we're going to plug it in for each x in the f of x function. So you could also write this as simply doing f of 3x. And the f function, it's going to square its input and then minus double its input. So what I've done is this structure right here, I just rewrote f, but I replaced the x and the x with empty sets of parentheses. And then in those sets of parentheses go this 3x now. So you have 3x here and 3x here. And then we'll simplify a little bit. 3x squared is 9x squared, and then minus 6x. This is fog of x. Now what we're going to do is find the reverse composition and change the input variable from x to t, just for variety's sake. When you do g of f of t, and we're going to take this function here, but t's instead of x's, so f of t will be t squared minus 2t, and we're going to plug that in for this x right here. What g does to an input, if you look at it this way, g takes an input and triples it. So what's g going to do to f of t? It's going to triple it. So g of this will be 3 times f of t, and then I can replace f of t with its expression, which is t squared minus 2t, and then I can distribute the 3 and say 3t squared minus 6t. Now, the input variables I switched from x to t, I could have left this one x, and the answer would have been 3x squared minus 6x. Notice it's not the same thing as the other direction. So the first thing we notice is that fog and goff isn't guaranteed to give you the same result. We can also do a composition of a function with itself. So this means we're going to be doing f of a. So we're going to take the f expression, which is over here. We're going to change the x's to a's to begin, and then we're going to plug it into itself. So f of a is going to be a squared minus 2a. But then we're going to take this, and it's going to get plugged in for that x and for that x. Both these x's here are now going to get this inputted for them. So what f does to an input, f takes an input, it squares it, and then it subtracts and it doubles it. And what's going to go in these parentheses here is just f of a. And f of a is a squared minus 2a. We have a squared minus 2a, and that's going to be squared minus 2 times a squared minus 2a. Now I'm not going to go ahead and FOIL this out. I will leave you to do that, but I just wanted to make sure that we understood how to compose a function with itself. Keep in mind, when I say the rule of a function, here's a complete function notation statement. We call f the name of the function. The x here is the input or argument of the function. So f of x represents the output, and the rule of the function's right here. This is the rule of the function. This tells you what to do to the input in order to yield the output. Next slide. Find two functions f and g such that m is equal to f of g. Give several possible answers. Okay, so m is the result of doing a composition. We just want to figure out what was plugged into what. And there's lots of ways to do this. One way to look at this is to think of what's inside the radical as a function in and of itself. I could say that g is equal to 3x minus 1. So then take this 3x minus 1, condense it back down to simply x, and then rewrite all of this, and we would call that f. So f function would look like 2 times radical just x plus 4. And then sure enough, if I were to do a fog, I would take the g function and plug it in for this x right there, would be replaced with that g of x, and it would turn into our m. So m is equal to the composition of these two functions. You could also just say that this part right here, the 3x, was the function g. So another option is to say that g is equal to simply 3x. So then the 3x in this position here, you'd condense it down to simply x, and then rewrite all of this, and that would be your f. So f would be 2 times radical x minus 1, and then plus 4. And then sure enough, if I take the g function and I replace the x and the f function with it, then we're going to get m again. So it is still true that m is equal to fog. Are there other ways to do this? Yes, lots of them. We could call all of this right here the g function. Or we can call just include the radical. Call that the g function. So let's say the g function is equal to the radical 3x minus 1. So then this part here, you're going to condense down to just x, and then rewrite this, and that would be your f. So 2x plus 4. And certainly enough, when I take the g function and I change the x and the f function with it, I get the m function. Okay, let's keep going. Just let g be x. Let f be m, essentially. Right, this is a trivial composition. If you take all the x's in f and change them to x's, you get f again, but you also get m. So it's still true that m is equal to fog in this case. Just to show you a variety, watch this. I'm going to let g be equal to 2 times the square root of 3x minus 1 plus 3. Now notice the m is plus 4. So if I were to take that 4 and break it apart into plus 3 plus 1, then you can see we have the g function right there. If I condense that g function down to x, then I would just have x plus 1 should be the f function. And sure enough, we'll get m by doing a composition of f of g. Right? Take this entire g function, plug it in for this x right here, and then add the 1 to this 3, and you get the 4. This alone should show you why we could get infinitely many answers here, because I could break 4 apart in many ways. I could, instead of saying 3 there, I could put a 5, in which case I want this to be a minus 1, so that the 4 comes out correctly. And so there's really infinitely many options just right here, playing with these constants. Okay, let's go to the next slide. The evaluation of a composite function can be thought of as a two-step process. Given the functions below, complete the table. Okay, two-step process. So we have a function u and a function v, and we are going to start with x is 9. And we're going to compute v of x. So we're going to plug 9 into the v function first. When you plug 9 into the v function's right here. So we're going to do square root of 9, and we're going to get 3. But now when we do composition, we take that 3 and plug it in as an input into the u function. So 3 goes into the u function, we get 1 over 9 minus 4, that's just 1/5. And so a visual that's often drawn for this kind of idea is that you can think of functions as sort of machines that transform numbers into another number. And you have like a conveyor belt. And if 9 enters the machine, it goes into the v function first and then the u function second. 9 enters the v function and it comes out a 3. But then 3 now enters the u function and it comes out a 1/5. 2 transformations to get through the u of v. And notice we go through v first. That sometimes is confusing when students see this and they write it. You write u first, then you write v, but you actually plug into v first and then you plug into u second. Now look at the 4. What does v do to 4? V will turn 4 into 2 because the square root of 4 is 2. And then what does u do to 2? U of 2, plug in 2, we get a 1 over 0. We get it does not exist because we got a 1 divided by 0. So 4 is a number that the first machine was successful. It transformed it into a 2, but as soon as 2 entered the u function, it broke it. u cannot handle the input of 2 because 2 is not in the domain of u. So 4 was not able to make the two-step journey. Let's try 1. Plug 1 into the v function. Radical 1 is 1. Now try to plug 1 into the u function. Not a problem. We get 1 over negative 3, so we get negative a third. So 1 made the two-step journey. How about 0? Plug 0 in. Can you do the square root of 0? The answer is yes. V will turn 0 into 0. And then can 0 be plugged into the u function? The answer is yes. You get negative 1/4. In fact, looking at the u function, there's only two values of x that u cannot handle. X squared minus 4 will only be problematic if x is 2 or negative 2. And so that's why we saw when we had a 2 here that we tried to plug into the u function, we had a problem. But also notice that because v is the square root of x, we're only ever going to get positive outputs of v anyway. You can never get a negative number in this position right here because v can't produce negative numbers. So you're never going to have a negative 2 trying to enter this u machine and breaking it. So that's making me think that 4 is the only starting value of x I can pick that'll lead to an intermediary 2 that will then break the next step. Let's try negative 4 though. If you try to plug a negative into the v function, right away we get not real. So we're going to say DNE because we don't get a real number. We get an answer of 2i. But as far as this chapter is concerned, we are back into the world of not accepting imaginary numbers as acceptable. And negative 4, in fact, no negative can be plugged into v. And if a number tries to enter v and breaks immediately, then it has no chance of successfully making through the second transformation. So we're just going to put a DNE here as well. Of course, all this would be different if we had said we allow for imaginary numbers. But we're saying no imaginary numbers, therefore negative 4 or any negative cannot be used in the first place. Okay, now the domain of a composition is the set of all input values. So everything in this column here that's possible that can yield an output following the two-step process. So if you start with a number here and you successfully get to a number over here, then we say that these x's are in the domain of this composition here. If it can't get through both steps, then it's not in the domain. So like think of 4, for example. 4 survived v, if you will. V turned 4 into 2, but then 2 couldn't produce a number over here. So 4 is not going to be in the domain because it couldn't ultimately yield an answer over here. Nor will any negatives, because no negatives can be plugged into v. And so our domain of this function would be x can't be negative, so it has to be bigger or equal to 0, but x can't be 4. And 4 is the only number that's positive that if you start with, you're going to get a number here that's going to break the u component. And you might see, if this is called set builder notation for giving the domain. So the domain is the set of all x such that, the little vertical line means such that x is an element of 0 up to 4, include 0, exclude the 4, union 4 up to infinity. So here's the very formal way to write down this domain. But all compositions are like this. You have to consider a two-step process and keep only the x's that can survive the two-step process. If you do the following, let's go ahead and write down what u of v is. So we're going to take the v function here, which is radical x, and plug it in for this x right here. So it looks like 1 over, and we get radical x, and that's going to be squared minus 4. If you leave your function like this, then your domain that we got over here still applies. Because there's a radical on the x, you can't use negatives. And we have to avoid a choice of x that might lead to a division by 0, which is 4. So again, I would say that x can't be negative, so it has to be 0 or positive, but it can't be 4. But here's the temptation. If you simplify that radical x and then square it and just write x minus 4, then all of a sudden you're going to get a new domain. So this domain that we got applies to the unsimplified version. The simplified version, maybe we should put a tilde on this because this is technically a new function. This simplified version has a domain of the only restriction is x can't be 4. Right? It can certainly be negative because once you get rid of the square root by squaring and you just write a simple x, all of a sudden this x here could be negative 5, not a problem. Negative 9, not a problem. So this function here, unsimplified, is technically different than this function here, simplified, because their domains are different. But when you're doing a domain of a composition, you want to give an answer that corresponds to the unsimplified version. This domain is the domain. Think of it as a two-step process. You have to be able to survive the first transformation and then subsequently survive the second transformation. Next slide. Use the table to find the values of the indicated compositions. Okay, so P of Q of 3. So this table here is just going to tell us what P and Q do to inputs separately. So we're first going to say this is going to be P of Q of 3. So we've got to figure out what Q of 3 is. So we track those two numbers right there. When the input is 3, Q turns it into 0. P turns 3 into 8, but Q turns 3 into 0. q of 3 is 0. But now we plug that 0 into the p function and see what we get. P turns 0 into 9. And so we get a final answer of 9. This was just a two-step process. We started with 3, q turned 3 into 0, and then p turned 0 into 9. Now let's do the reverse, q of p of 2. So this time I'm starting with x equals 2 and plugging into p first. So x is 2, and plug that into the p function, and we get 1. So we have q of 1. And now plug 1 into the q function, q turns 1 into 5. So we get a final answer of 5 here. We could do something similar by using a plot instead. Use the graph to find the values of the indicated compositions, w of z of 3. So we're going to say, well, what's z of 3? We're going to do that first and then plug that into the w function. So let's first figure out what z of 3 is. So we're looking at this function right here. That's the z function. Track down 3 as an x-coordinate, and then look for what z does to 3 by looking for that second coordinate. And that second coordinate is 2. So z will turn 3 into 2. So z of 3 is 2. Now we want to say, well, what's w of 2? Now we look on the w curve, which is this parabola curve there, and when the input is 2, the output is 0. All right, so w turns 2 into 0. So we get 0 as the final result. Again, a two-step process. 3 was turned into 2 by z, and then 2 was turned into 0 by w. And then the reverse composition, let's do z of w of 4. So we're going to start with 4 and plug that into the w function. So there's a point right here. It looks like it's 4 comma 1. So w turns 4 into 1. So we have z of 1 is what we want to do. Also notice that I cross my z's. Otherwise, my z's and 2's look alike. Anyway, now we want to do z of 1. There's a point on the z curve right there, 1 comma 3. And so it looks like z will input 1 and output 3. A circle initially has a radius of 3 inches. It begins to expand in such a way that the radius gains 2 inches every 30 seconds. Fill in the table below. So at time 0, the radius is 3 inches. It expands in such a way that the radius gains 2 inches every 30 seconds. Okay, so every 30 seconds we gain 2 inches, so that means every minute we gain 4 inches. A minute has gone by from 0 to 1. So we have to gain 4 inches and go to 7. And we just keep gaining 4 inches. Add 4, so we have 11 inches, and then add 4, 15 inches, and then add 4, 19 inches. Now, if you recall the formula for finding the area of a circle, pi r squared. So if I know the radius at any moment in time, I can find the area. I just do pi times the radius squared. So pi times 3 squared will be 9 pi. This is measured in square inches. Pi times 7 squared will be 49 pi. Pi times 11 squared is 121 pi. Pi times 15 squared is 225 pi. And I'm going to need a calculator to do the next one. 19 squared is 361. So these are the different areas we get at the different moments in time. Okay, now we're going to express the radius as a function of time. So radius is gaining 4 inches every minute. So we know that the radius r as a function of time, so r of t is what we want to create here. Put a rule here that only involves t. How do I use time to find my new radii? Well, it's a linear growth. We're gaining 4 inches every minute. So it's going to be 4 times the number of minutes, and then plus the radius at time 0, which is 3. Just double check that real fast. See if this part of the table gives you the correct values when you use this rule. Right? When t is 1, we get 7. When t is 2, 4 times 2 is 8, plus 3 is 11. When t is 3, 4 times 3 is 12, plus 3 is 15, etc. So this is the correct r function as a function of time. Now express the area as a function of radius. So area as a function of radius, well, I've already written that. It's just a pi r squared. And this is area as a function of radius. Now express area as a function of time. And here's where composition comes into play. Well, a of t is what we're after. And we're going to get it by doing a of r of t. In other words, we're doing a composition. We're doing a little o r of t. This is the composition notation. And all that's happening here is a substitution. We're taking this 4t plus 3, which is the r function, and we're going to plug it in for the r's in the area function. So we're going to get pi times r of t squared. In other words, we get pi times, and r of t was 4t plus 3, and that's being squared. And so we can see a composition was needed to use here to get this formula for what the area is at any moment in time. And let's just test one of these. Let's test this entry right here. We're going to see if plugging in t equals 3 gives me the correct area of 225 pi. Or you plug in 3 for t in this spot. We get 12 plus 3. That's just, we get a 15 there. Then we square that. We get 225 and then times pi. And we get our 225 pi as expected. All right, and this concludes our lesson on composite functions.